In contrast to GNN node, GNN graph will have a set of pooling layers. And ultimately, we'll apply this GNN graph. If we have a model parameters, we can learn output feature vector fg corresponding to Gth graph. How we can actually do that? Once we actually use the label information to actually do that. For that, we are going to define, like for the node classification, we will actually define a softmax layer which actually in which we have to learn theta2 parameters, which transforms the feature dimension to a number of classes, or output will be again logits for a particular graph. Unlike node classification, here we will have for each graph we have a vector 1 cross C. There, if you recall, we have for each node we have it. Here for each graph we have it, and since our input is each graph in dataset D, the Z will be a vector of probability distribution of different classes depending on the problem. It can be binary, it can be multiple classification problem. Once we have this Z, we can actually predict the class associated with G. Before that, we have to learn this parameter theta1 and theta2. Same way in a graph node classification, we do in a graph classification. The model parameters are learned by minimizing loss over a labeled graphs. Again, we are going to use minimization of cross entropy losses. Here, yi is the graph label, theta are the theta1 and theta2 total model parameters, f GNN is a graph model we are using for this particular graph classification problem, L is a cross entropy loss function, and we are summing this over all the graphs in my data set D with labels yi. So we are trying to minimize for each graph total and learn parameters theta and theta2, and loss function here is a loss summed over all the training samples. So we look at it, how graph classification is performed once we have graph. We'll have here input graph with A as the adjacency matrix, F in as a input features for each of nodes. We'll apply set of filters and pooling functions, or we'll do set of filtering and pooling operations to obtain intermediate coercent graph and corresponding adjacency matrix and feature vector. Here we can define, if we want to distinguish between F in and F out, A in and between adjacency in and adjacency out, like F in and F out, we can do also A in and A out. However, it is very clear from the dimension of these two matrices that this has a less number of nodes, and these super nodes can be further coerced by applying filtering and the pooling operations and get a final feature for this particular graph. Now remember that by minimizing the loss function for label data, we actually have learned theta1 and theta2, so we can actually use the same GNN to move from the for unknown graph, unknown label graph. We can pass through this filtering operation of GNN, this filtering operation of GNN, and get a feature for that. Let's say GU. So this is a feature for GU, and this feature will be passed through softmax layers. Let's look at a graph classification case study. Here, the first case study deals with the enzyme datasets. So in a cell, there are certain enzymes, several enzymes, which actually catalyze different class of chemical reactions, and those chemical reactions are then perform certain metabolic tasks. Now it is important to understand what kind of enzyme will catalyze what kind of reactions. It has implications in producing different kind of biotechnologically induced products or some kind of medicines depending on the applications. So what we have here is a data set consists of 600 protein ternary structures. So protein has a different structures, and here like primary, secondary, ternary, etc. And we are looking at ternary structure information for these 600 proteins, and there is a very famous Branda database available to all of us. From that, these structures are recovered, and each of this protein structure is associated with 6 classes of chemical reactions which this particular enzyme can catalyze. So enzyme is represented as a protein ternary structure, and with each structure we have actually associated a particular label, which is nothing but whether this particular which kind of reaction this particular enzyme catalyzes in the field. And the objective here is, if I have a new protein tertiary structures, I want to know which kind of reactions that this particular protein will catalyze. So nodes of secondary structure elements are considered as nodes, and the node feature here is considered as one hot encoding for their secondary structure element, either helix, sheet, or turn. The edge here is connection between two neighboring amino acid along the sequence. So connected if the neighbors along the amino acid is in acid sequence, otherwise not. Here we have an average in a data particular graph. We have around 32.63 nodes and around 124 edges in the graph. So here each of this node, as we discuss SSE, and for that we have depending on their secondary structure element, we have either one hot encoding for different 100. Let's say it's a helix, sheet, and turn. Then if it's a helix, it's 1. If otherwise another remaining are 0. Let's say here in this one node we have turn, then HST, there's a 0, 0, 1. Now using this data, we are going to actually use graph neural networks to develop a classifier for new enzyme. So what we have done is we have done a stratified split where training has 80%, test has a 20%, and stratified split ensures the proportion of different labels. Number of filters we have used is only 2. We can use more filters, and the hidden channels are 32. Okay, so D out in between is a 32. In case of optimizer, we use Adam W with learning rate equal to 0.001. We run this particular model for 20 epochs, and after that we have actually tested it on this 20% data sets using the trained model with different kind of graph neural network like GNN, GCN, GATE, and GraphSage. These are different kind of filters. I'm not discussing pooling operations. We can use any pooling operations, but we are using currently a simple pooling operation with this as my filters. And if we compare the performance using area under the curve of ROC, we can see that the performance of GC and GAT is comparable. However, GNN performs quite poor. GraphSage is not bad, but it cannot actually beat the GCN and GAT. And absolutely, the GC and GAT graph attention network provides a bit better performance than GCN when it comes to AUC ROC. Of course, I can actually do more hyperparameter tuning and figure it out the performance of different node, but with this setting, GAT is or graph attention network performs better than any other filter based GNN.